Hello and welcome to our lesson on absolute extrema. And we have talked about relative extrema, so now we're going to do a comparison between those and the absolute, which means we're also going to have to talk about a distinction between open intervals and closed intervals. So let's try to make some connections to our previous learning and then build. So an open interval to start with just means we're looking at an interval or a portion of the graph, some neighborhood, that does not include the endpoints of that interval, or it could be possible that the ends are going off to positive or negative infinity. So an open interval, again, does not include its endpoints, and positive and negative infinity would never be included in an interval because they are locations that intervals are approaching. Okay, if we're looking at an open interval of a graph, it may or may not have any extrema. If I have a graph, for example, that goes up forever, there won't be a maximum absolute on that interval. Okay. Now, I just threw that word in there. We haven't talked about it just yet, but I think you're getting the concept. But stay with me. So extrema, we have talked about, refer to the maximum and minimum points in our graph. So these are our maximums and our minimums. And we have seen how these maximums and minimums, I dotted the U there, are occurring at turning points. So places where our graph turns from increasing to decreasing or vice versa, we have a maximum or a minimum. And we have talked about the relative ones because we had previously looked at, again, open intervals. Now, if we're talking about an extremum that is the largest value or the absolute highest point on the graph, then we're not going to just call that extrema a relative maximum. We're going to call it the absolute maximum. If there is no point that is higher than that absolute maximum point, again, absolute maximum. So if it's the largest value, our output is the largest value, or if it's the highest point on our graph, it is going to be referred to as the absolute maximum value or absolute maximum point of that graph. And the same for the other end. When our extremum is the smallest value, so that we have the smallest output, or it is the lowest point on the graph, there is no point lower than that point, no value smaller than that value, that output, then that is going to be our absolute minimum. Now, if we have any turning points that are not absolute maximums or minimums, they are not the highest or lowest points on our graph, then those are our relative or local maxes and mins. So there's our distinction. Okay, on an open interval, we can have the absolute highest point, the absolute lowest point, and any other turning point in between is just a relative or local max or min. Now, sometimes these things coincide, they correspond. I was trying to put two words together there. So we could have an absolute maximum that we would refer to as a relative maximum, and same for the minimums, and I don't know, vice versa, whatever I'm saying. So absolute extrema, they often coincide or correspond with our relative extrema. So again, I could call one the other sometimes, and it is definitely possible for our function to have several relative extrema. So we could have multiple relative maxes, multiple relative mins, but there can never be more than one absolute max or one absolute min, and we've already said that it may be possible to not have any at all. So let's just look at a couple of graphs just to wrap our brains around the concept, okay? So we know how already to distinguish between maxes and mins. So if we are going from decreasing to increasing like we are doing here, then we know that this point represents a minimum. And if we're going from increasing to decreasing like we are at this next turning point, that we have a maximum. And again, this one's going from decreasing to increasing, so we have another minimum. So we know how to identify maxes and mins. Now, in this particular graph, there is, we could call these two minimums both relative minimums, and we can call that maximum a relative maximum. But we can also refer to the relative min here as an absolute minimum because there is no point that is lower than that point. That is absolutely the lowest point on that graph. So these are all relative extrema, but we could also call this one an absolute min because, again, it is the lowest point on the graph. And there is no absolute maximum on this open interval because the two ends of the graph go up forever, so there will always be some higher point. Again, no absolute maximum. Okay, so looking at the next picture, again, we're going to go from decreasing to increasing and then back to decreasing. So I can see here I have a minimum and here I have a maximum, and both relative, okay, relative min, relative max. Neither one of these could be classified also as an absolute because this graph goes up forever and goes down forever. There is no absolute highest point and no absolute lowest point. So those are both strictly relative maxes, mins. Okay, here our graph goes from increasing to decreasing, and so this is going to be a maximum, and again we could call this a relative maximum on this open interval relative to that location, but because it is the highest point on this graph, there's no point that is higher than that point, we can also refer to this as an absolute maximum. Okay, and no absolute minimum because this graph goes down forever. Now if you look here, we have this linear function that is increasing over its entire domain from negative infinity to positive infinity, and there are no turning points in between there. So since the graph goes down forever and goes up forever, there isn't an absolute max or min, and because there are no turning points in between, we have no extrema. So no extrema on this linear portion here. Now, if we were to chop that linear function and just look at a segment of it, so instead of having arrows that go infinitely in both directions, does that mean we have extrema? Well, if it's a closed interval, which we'll talk about in a second, yes, but if this interval is open, which is what these endpoints being open here tell us, that means we're not including those endpoints, we still have no extrema. So let's just say, like, if this is on a graph, and this was going from like -2, let's put this up here, from -2 to, let's say, +2, and that's way off, but whatever. If I said, look at the interval from -2 to 2, that's an open interval. These parentheses are saying do not include those endpoints. That means our ends are approaching a minimum value of -2 and approaching a maximum value of +2. But because I can't quite get there, can't include those, there are infinitely small decimals in between every point I pick and those not included endpoints. So if it's an open interval, no extrema on those linear graphs. Okay, open intervals, if there are no extrema, if we have no turning points in between the ends. Okay, hopefully that makes sense. And I want to get rid of all this nonsense I drew here. Okay, so now if we're dealing with a closed interval, it's a little different. A closed interval means we're looking at an interval where the endpoints are included. So a closed interval is an interval that includes its endpoints. So if we're including the endpoints, that means we are starting at a specific location and stopping at a specific location. That means we must have, if it's continuous, okay, I forgot that little disclaimer, if we have a continuous function that is on a closed interval, we must have an absolute maximum and an absolute minimum on that interval. That's something that we refer to as the extreme value theorem. That gets proved a little later in, not this calculus class, but I don't know if it's Calc 1 or Calc 2, but those proofs happen in other levels or other branches of calculus, and there are lots of useful applications to that theorem. But for our sake, on the closed interval that we're looking at, we have to have an absolute max and absolute min. The question is, where could it happen? Well, it depends on what the graph looks like, but we are still going to be able to narrow where these happen. So let's say we have some continuous function and there's like one turning point in between. We have the absolute highest point of the graph here, so that's our absolute maximum, and the absolute lowest point at the turning point in between those two endpoints, that's going to be our absolute min. So we could have our max and min happening at an endpoint, we could also have it happening at a turning point. And we have a linear portion here, so since there are no turning points, the absolute max and min happen to be at the endpoints. Again, different from what we saw before because these endpoints are now included in the interval. This is absolutely the lowest point, this is absolutely the highest point on that interval. Okay, now we have in this next one a few different turning points. So we have a max, and then we have a min, and then we have another max, and then we have our endpoints. Well, neither one of those endpoints is our max or our min. The absolute highest point here happens to be this turning point, and the absolute lowest point here happens to be this turning point. Okay, but if we're looking for absolute extrema on a closed interval, there are limited places where they could happen. They happen at our could happen at our turning points, and they could happen at our end points. So on a closed interval, we have to have these absolute extrema, and they have to happen at either the end points of that closed interval or at the relative extrema that are happening in between that closed interval. So it's one of those two places where we see our max or we see our min. So algebraically, how do we go about finding these? Well, we know how to find our relative extrema already, and we can figure out the function values at our endpoints by just evaluating our function at those endpoints. So if we're going to try to algebraically find our absolute extrema, again on a closed interval that starts at a and ends at b, we're going to find the critical numbers of the first derivative, because remember what those do. The critical numbers of the first derivative, those tell us where the slope of our function is 0 or undefined. Those are our turning points, okay? If we can find the critical numbers of the first derivative, then we will be able to locate our relative maxes and mins, but we want to make sure that when we identify those, we're only looking at the ones that lie in the interval. So if we have a critical number that's outside of the interval we're looking at, it does not apply to our problem. And then we want to evaluate our function. Let's evaluate our function at those critical numbers and also at the endpoints of the interval. So we're going to actually take the critical numbers and plug them into our function and see what the output is. We're going to take the endpoints of the interval. Remember, these endpoints, these are x values. We're going to plug those into our function and see the function values, and then just compare. Whatever input produces the largest output is our absolute maximum, and whatever input produces the smallest output is going to be our minimum. So the smallest value will be produced by the absolute minimum. That's still my highlighter. And the largest value, the largest output, will be produced by the absolute maximum. And then we have a few different ways that we can kind of answer the question, but let's practice this, okay? So without graphing, by using algebra, let's find the absolute extrema of each function over the specified interval. So here's a quadratic function. We're just looking at the interval from 0 to 5. Remember, this is an x value and this is an x value. So starting at x equals 0, going to x equals 5, do we have any extrema? Well, let's find or any absolute extrema. Yeah, we do. Let's find them. So we're going to start by finding our first derivative. So that's going to be a 2x minus 6, and the critical numbers make this first derivative either equal 0 or undefined. We can't make this undefined, but we can make it equal to 0. We can make 2x minus 6 equal 0. If we add the 6 over and divide the 2, we see x equals 3 as a critical number. So remember, our absolute extrema are going to happen either at these critical numbers or at the endpoints of our interval. So I need to plug in this critical number to my function, this critical number into my function, and this critical number into my function. And the largest output tells me where my max is, and the smallest output tells me where my min is. So now I need to find three things. I need to find my function value, so into my original function, my function value at 3, my function value at 0, and my function value at 5. So plug in the critical numbers and the endpoints of the interval into the original function. So let's do this. We plug 3 in. 3 squared is going to make 9.
Negative 6 times 3 is negative 18, so 9 minus 18 would be negative 9, plus 2 is going to make a negative 7, and by all means use a calculator for that if you want to. Plug in a 0, that's going to give us a 2, and then plug in a 5, we're going to have 25 minus 30, so negative 5 plus 2, which would be a negative 3. Okay, so based on these results, this is the smallest output that's produced, which means here is where we have our absolute minimum. And this is the largest output that is produced, which means this is where we have our absolute maximum. So we could say this a few ways. I could say I have an absolute minimum at x equals 3, or I have an absolute maximum at x equals 0, or I have an absolute minimum value of negative 7, or an absolute maximum value of 2, or I can say I have an absolute minimum at the point 3, negative 7, or I have an absolute maximum point at the point 0, 2. Absolute max at the point 0, 2. A little redundant there. Okay, so just so we can see the variety in ways we can answer, I could say I have a minimum value of y equals negative 7, so the minimum actual value, that's the output, that's the y, and it's produced at the x value that we plugged in was 3. So I could say it's a minimum value of negative 7 that happens at x equals 3, or there's an absolute minimum at the point 3, negative 7. And the same for the, yeah, that's right. I was going to say I got the max and mins mixed up, but I did not. So then we could say we have a maximum value of y equals 2, and that happens at an x value of 0, where we can say there's an absolute maximum point at 0, 2. Okay, so there's the algebra involved, which is pretty easy for this one. But remember, your graph shows you all the information you're looking for, so you might as well confirm what you're doing with Desmos. So let's look at x squared minus 6x plus 2. Now remember, we're only looking at the interval from 0 to 5, so I'm going to go ahead and put that in here just to make sure we're looking at the correct portion of the graph. So I'm going to go from 0 less than or equal to x less than or equal to 5. So here's our graph. So what we're saying is the maximum happens here, and there it is. That makes sense. That's the absolute highest portion of that graph. That's when our x is 0 and our y is 2. And then here's our minimum, x value of 3, y value of negative 7. Okay, so it's obviously really easy to get the information from the picture, but now we have the algebra that goes with that picture. Okay, so let's try it again, because not all derivatives are quite so simple. So let's look at this next one. Over the interval from negative 2 to 3, let's find our absolute extrema. Derivative f prime of x is going to use our power rule and our chain rule, so we're going to multiply by a third here. Keep this inner function as is, subtract 1 from our exponent, so 1/3 minus 1, or minus 3/3 would be negative 2/3. And then we multiply by the derivative of the inner function, so the derivative of x squared minus 4 would be 2x. And then we don't have to clean this up, but I'm going to because I need to find the critical numbers. Doing a little solving would be easier if I made this look a little nicer. So f prime of x is going to equal, the 2x is going to be on the top of the fraction, the 3 is going to be on the bottom. I'm going to go ahead and move the x squared minus 4 to the 2/3 to the bottom, because it's got a negative exponent. And I prefer radicals to those rational exponents, so I'm going to make that the cube root of x squared minus 4 squared. But you don't have to do that. This is just for my own preference, how I would like this to be set for me to solve. Because remember, what I want to do is find the critical numbers of this derivative. So that is, where is it equal to 0 and where is it undefined? So where is my derivative going to be equal to 0? So f prime of x equals 0. Let's do that work. That's going to happen when our numerator of our fraction is equal to 0. So when 2x equals 0, which means x has to be equal to 0, that's going to be one of our critical numbers. Now, we also know we have critical numbers when our function is undefined. So where is, or derivative is undefined. So where is this going to be undefined? Well, in the last one we had a polynomial that we could not make undefined, but here we can definitely make this fraction undefined if we make our denominator equal 0. So where is 3 times the cube root of x squared minus 4 squared? Where is that going to be equal to 0? Well, you could divide the 3 over, you can cube both sides to get rid of the cube root, you can square root both sides to get rid of the square there, but all that's going to happen to the 0, which means ultimately we need to know where x squared minus 4 is going to equal 0. So if we add the 4 over and then take the square root, we're going to get a positive and a negative 2. Now the 0 and the 2 and the negative 2 all within this interval, so all of those critical numbers as well as these endpoints have to be plugged into my original function now to figure out where our extrema are going to be. So I need to find my function value at 0, at positive 2, at negative 2, so those are my critical numbers, and then at negative 2 and at 3. Well, negative 2 I've already got here, so let's find our function value at 3. Okay, so these are the pieces I need. Now I don't want to have to deal with actually calculating this, so I'm going to put this into my calculator. Let's go here with something squared minus 4, and then raised to the 1/3 power, and then that's it. So we just need to input into our function. Let's start with a 0, and that gives us approximately negative 1.59, and then let's change that to a 2, and then we get a 0. Let's change that to a negative 2, get a 0 again, and let's change it to a 3, then we get approximately 1.71. Done. So this is my minimum output here, which means I have an absolute min at the point 0, negative 1.59, or at x equals 0, or an absolute minimum value of negative 1.59. And then this is the maximum that's produced. So here's my absolute max. So I can say I have an absolute max at the point 3, 1.71, or a maximum value of 1.71, or a max at x equals 3. So all those different ways we can answer, but these are the results. Okay, so this is the important information here, this is the important information here, and let's go ahead and just confirm this on a graph. So here's our original function. We said let's look at the interval that goes from negative 2 to 3. So negative 2 less than or equal to x less than or equal to 3. And clearly the maximum happens here at 3. That's exactly what we said. And there's our minimum at 0. And again, exactly what we said. So really easy to get the information off the graph, but we have the algebra now that goes with it. All right, let's try this again. Just differentiating with a variety of ways. So here we're going to be using our quotient rule to differentiate. So we got f here, we got g here. Remember the quotient rule? F prime g minus fg prime over g squared. So f prime of x is going to equal f prime, so derivative of 1 minus x is just going to be a negative 1, and then g is x plus 3 minus f, which is 1 minus x, times g prime, which will just be a 1, and then we're dividing by g squared. And again, it's not really necessary to clean this up because I know I'm finding critical numbers and doing a little bit of solving. I'm going to go ahead and do that. So f prime of x equal to a negative x minus 3 and then a negative 1 plus x, just distributing in that numerator. And then combining like terms, we end up with f prime of x equal to, the x's are going to cancel, so just a negative 4 in the numerator, and then x plus 3 squared in the denominator. So my critical numbers happen where f prime of x, my first derivative, is equal to 0. So if I wanted to figure out where this would be equal to 0, I'd be trying to make my numerator equal 0. Well, that's not possible, so there's no solution here. But I can also try to figure out where my derivative is undefined. And that can happen when the bottom of my fraction is equal to 0. So let's figure out where x plus 3 squared is equal to 0. If we square root both sides, I'm just looking for x plus 3 to be equal to 0, which means negative 3 is going to be our critical number. Now notice negative 3 is not in our interval. So even though it's a critical number, it's not going to apply to our problem. So that is not in the interval. That means that the absolute max and the absolute min for this piece of the graph that we're looking at here have to happen at these endpoints. So we need to evaluate our function just at those endpoints and we'll be good. So let's find f of 0 And let's find f of 3. And maybe we can do this without the calculator. Yep, I can plug a 0 in for both those x's, and I'm left with positive 1/3. If I plug a 3 in, I get negative 2 on the top and 6 on the bottom. And negative 2 over 6 is going to be a negative 1/3, which means this is going to be my maximum. And this is going to be my minimum. And remember the variety of ways in which we can say those answers. So I have an absolute max at x equals 0, or an absolute maximum value of 1/3, or an absolute max at the point 0, 1/3, and it's the same for the minimum. Let's just confirm. So I'm graphing my rational function with 1 minus x in the numerator and x plus 3 in the denominator. And we're just going to look at the interval from 0 to 3. So 0 less than or equal to x. Oops, forgot the 0. And then less than or equal to 3. Okay, so this is a little piece of the graph we're looking at. So again, you can see in that interval no turning points, so no extrema in that interval. So our max and min happen at the endpoints. There's our max at 0 and 1/3, and there's our min at 3 and negative 1/3. Piece of cake. All right, we got one more, again, just for a variety of differentiation. Let's look at this. I know everybody's favorite with the product rule and the e to the x in there. Hopefully you're recognizing product rule. So we have one function here in x squared. We have a second function here in e to the negative 0.5x. So product rule is f prime g plus fg prime. So let's go ahead and find our derivative. So f prime of x. So we need the derivative of x squared, which is going to be 2x. That's going to be multiplied by g, which is our e to the negative 0.0, nope, just kidding, negative 0.5x. And then we're going to add on f, which is x squared, times the derivative of g. Now the derivative of e to the x is just e to the x, so that's going to be e to the negative 0.5x. Now because that is not just an x there, we're going to multiply by the derivative of that inner function, and the derivative of negative 0.5x would just be negative 0.5. So if I make this a little bit cleaner, 2x e to the negative 0.5x plus minus 0.5x squared times e to the negative 0.5x. Now it would be totally acceptable to leave this in this form, although I probably would take this another step if maybe a couple of steps here. Factoring would be helpful for the process of solving that we're going to get to, and we can definitely take out an e to the negative 0.5x here, and then we're dealing with the 2x that's left and the negative 0.5x squared, and factored form would be perfectly acceptable too, but this negative exponent here I would probably fix as well. So I'm going to go one more round, and wherever you want to stop is totally okay for you. I just would prefer this version of it myself. So I'm going to move this e to the negative 0.5x here, and now that it's on the bottom, it's not negative. Let's do this correctly. So here's what we're looking at, okay? I want to know where is that derivative going to be equal to 0. This is one of the reasons I moved this, because I know that's going to be where my numerator is equal to 0. So f prime of x is going to be equal to 0 when my numerator equals 0, so negative 0.5x squared plus the 2x, where is that going to equal 0? I'm going to go ahead and divide this equation by the negative 0.5 that's in front of the x squared to make the solving a little cleaner for myself. So x squared plus, just kidding, it's going to be x squared minus, how many halves are in 2 would be 4, so minus 4x equal to 0, and that factors into an x and an x minus 4, which means my solutions would be 0 and positive 4. And those are two critical numbers that are in that interval, so we're going to keep those. And then we also want to see if we can make our derivative undefined. Now I can make my derivative undefined if I can make my denominator equal 0. So if e to the 0.5x can equal 0, I would get another critical number. However, I cannot make this exponential function equal 0. If you know the graphs of your exponentials, that's an easy one to see, but no matter what power you raise e to, whether it's a positive power or a negative power or 0, you're going to get When you raise anything to the power of 0, you get 1. When you raise it to negative numbers, you get fractions. There's just no way to make that negative, or to make it get to 0. You're going to get smaller and smaller fractions, but approach 0, not get there. So there's no solution to this one. So we've got our 2 endpoints to plug in. Oops, just kidding. We don't have... Well, we have our 2 endpoints to plug in. We have the one critical number. 0 is not in the interval, so I don't have to worry about this one. So this one's not going to apply. It's not in our interval. So we need to find our function values at 4, 2, and 5. So let's find f of 4, f of 2, and f of 5. And I'm going to do this work in my calculator. So I'm going to put in my x squared and then e raised to the negative 0.5 times x. Okay, so first I'm putting in an x value of 4, and I'm going to get approximately 2.17-ish, and then I'm going to put in a 2, and I'm going to get about 1.47, and then I'm going to put in a 5, not a 25, a 5, and get about 2.05. Okay, so I have my maximum output here. This is going to be my absolute maximum at x equals 4. And I have my minimum here, so this is going to be my absolute minimum at x equals 2. And again, let's just confirm. Let's put our function in here. I'm going to put x's back in. And we're only looking from, I forgot, 2 to 5. So let's put our interval in. Y. Calculator sometimes. Alright, so we're going to go from 2 less than or equal to x less than or equal to 5. Okay, so where is our maximum? We can see that maximum point happens there. We set at x equals 4, perfect. And this is our lowest point on our graph, so our minimum happens at x equals 2, and we can see the corresponding outputs being precisely what we said. So there's our work verified. Again, we have the graph that easily gives us the information, but now we also have the algebra to solve for that information. Okay, so probably the trickiest part here is actually the calculus of finding the derivatives. The actual work of figuring out where a max and min is not so bad. So I think you got enough to get going on your assignment, but as always, if you need some help, then just reach out. Until next time, take care.